Determinant of a matrix of order 2. Welcome, everyone. Before we dive into today's new topic, let's quickly recap what we've learned so far. In our previous lesson, we established that a determinant is a single scalar value, essentially just a number, that is uniquely associated with any square matrix. Now, today, we are narrowing our focus. We are going to look specifically at the determinant of a matrix of order 2, which you might also hear referred to as a 2x2 matrix. You'll find that the calculation for this specific type is quite straightforward, and mastering this simple process is essential, as it serves as the fundamental building component for understanding much more complex, higher-order determinants later in this course. Let's get started. Understanding the structure. A square matrix of order 2 is quite simple. It consists of exactly 2 rows and 2 columns. To make our calculations easier to follow, let's define a general matrix, which we will call matrix A, as follows. Matrix A, with its first row containing elements a sub 1-1 and a sub 1-2, and its second row containing elements a sub 2-1 and a sub 2-2. To master the formula we are about to learn, you need to recognize 2 specific parts of this matrix. First, look at the elements a sub 1-1 and a sub 2-2. These run from the top left to the bottom right, and we call this the main diagonal. Next, look at the elements a sub 1-2 and a sub 2-1. These run from the top right to the bottom left, and we refer to these as the off-diagonal elements. Keeping these 2 paths distinct is the secret to calculating the determinant correctly in the next step. Now that we know a determinant is a single scalar value, let's take a closer look at the structure of the matrix we are working with. The determinant formula. The determinant of matrix A, which you will see written in your textbooks either as the letter A enclosed in vertical bars or as det of A, is calculated by finding the difference between 2 specific products. Specifically, we take the product of the elements on the main diagonal and subtract the product of the elements on the off-diagonal. To put this into a formal mathematical formula, we say, the determinant of it equals a sub 1-1 multiplied by a sub 2-2 minus a sub 1-2 multiplied by a sub 2-1. Now that we have identified the structure of our matrix and labeled our elements, let's look at how we actually compute the value. In the next slide, I will break this down into a simple, step-by-step process so you can apply this formula to any matrix you encounter. Step-by-step calculation process. Now that we understand the structure of our matrix and which elements belong to the main diagonal and the off-diagonal, let's break down the actual calculation into a clear, 3-step process. This will ensure you don't miss any parts of the formula we just saw. First, let's look at step 1, which is identifying the main diagonal product. You'll want to and focus on that line running from the top left to the bottom right. Take the element located in the first row, first column, which we call a 1-1, and multiply it by the element in the second row, second column, which is a 2-2. We can call this result product 1. Next, we move to step 2, where we identify the off-diagonal product. Here, we look at the other diagonal, running from the top right to the bottom left. Multiply the element in the first row, second column, known as a 1-2, by the element in the second row, first column, which is a 2-1. We'll refer to this result as product 2. Finally, in step 3, we perform the subtraction. To find the determinant of matrix A, which we denote as the absolute value of A, you simply take product 1 and subtract product 2 from it. By following these steps systematically, you'll be able to handle any 2x2 matrix, even when we encounter more complex numbers or negative values, which we will explore in our next few examples. Real-world application, area of a parallelogram. Now that we have mastered the formula and the step-by-step process, let's look at why this matters in the real world. Determinants aren't just abstract numbers. They have powerful applications in coordinate geometry, specifically for finding the area of a parallelogram. Imagine you have 2 vectors starting from the origin, which is the point 0, 0, and extending to 2 different points. Let's call them x sub 1, y sub 1, and x sub 2, y sub 2. If you use these two vectors to form the sides of a parallelogram, the area of that shape is simply the absolute value of the determinant of a matrix created using those coordinates. Let's walk through a concrete example to see this in action. Suppose we have a parallelogram defined by two vectors, vector v sub 1, which is 3, 1, and vector v sub 2, which is 2, 4. We can arrange these coordinates into a square matrix, which we'll call matrix M, where the first row is 3, 1, and the second row is 2, 4. To find the area, we follow the exact same steps we practiced in the previous slides. First, let's identify our elements. Our top left element, a sub 1, 1, is 3. Our top right, a sub 1, 2, is 1. Our bottom left, a sub 2, 1, is 2. And our bottom right, a sub 2, 2, is 4. Step 2, we calculate the product of the main diagonal. That is, 3 times 4, which gives us 12. Step 3, we calculate the product of the off-diagonal. That is, 1 times 2, which gives us 2. Finally, step 4, we subtract the off-diagonal product from the main diagonal product. So, the determinant of matrix M, written as the absolute value of M, is 12 minus 2, which equals 10. Because the determinant is 10, the area of our parallelogram is exactly 10 square units. Now, keep in mind that while this example used positive numbers, the next slide will show you how to stay careful when dealing with negative values. Numerical example with negative values. Now that we have seen how this works with positive numbers in our previous example, let's look at something a bit more challenging. It is crucial to handle signs carefully when elements are negative, as this is where many students run into trouble. Let us find the determinant of matrix B here. We have matrix B, which consists of negative 2 and 5 in the first row, and 3 and negative 4 in the second row. Let's walk through the step-by-step solution together. First, we identify the main diagonal product. We multiply the element in the top left, which is negative 2, by the element in the bottom right, which is negative 4. Remember, a negative times a negative gives us a positive, so negative 2 times negative 4 equals 8. Second, we find the off-diagonal product. We multiply the top right element, which is 5, by the bottom left element, which is 3. This gives us 15. Finally, we perform the final subtraction. We take our first product, 8, and subtract our second product, 15. So, the determinant of B, written as the absolute value of B, equals 8 minus 15, which results in negative 7. As we move to the next slide, I want you to pay close attention to how those negative signs can change your final result, as we will discuss some common pitfalls to avoid. Common mistakes to avoid. First, watch out for incorrect diagonal pairing. I have seen many students mistakenly multiply elements that are in the same row or the same column. To avoid this, always visualize the X shape. Always remember, it is the top left element multiplied by the bottom right element minus the top right element multiplied by the bottom left element. Second, be extremely careful with sign errors during the subtraction step. This is where most marks are lost. Remember, you are subtracting the entire second product. So, if your off-diagonal product happens to be a negative number, that subtraction sign will turn into addition. For example, if your main diagonal product is 10 and your off-diagonal product is negative 5, your calculation becomes 10 minus negative 5, which simplifies to 10 plus 5, giving you a final result of 15. Always keep a close eye on those double negatives. Finally, do not confuse the matrix itself with the determinant. A matrix is simply the rectangular arrangement of numbers, which we write enclosed in square brackets. However, the determinant is the single scalar value we are calculating, and we denote it using vertical bars. Keeping this distinction clear in your notation will help you stay organized as we move on to more complex topics. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the formula, it is very easy to make small errors that lead to the wrong answer. Let's look at 3 specific mistakes to watch out for. In our final slide, we will summarize everything we have learned today. Key takeaways. First and foremost, always remember that a determinant is only defined for square matrices. This means the number of rows must exactly match the number of columns. You won't find a determinant for a rectangular matrix. Next, let's recap the core formula we've been working with. For a 2x2 matrix, which we've called A, the determinant of A is equal to the element in the first row, first column, multiplied by the element in the second row, second column, minus the element in the second row, first column, multiplied by the element in the first row, second column. It is that specific pattern of the main diagonal minus the off-diagonal that we must always follow. Third, keep in mind the nature of your final answer. As we saw in our examples, both with the area of the parallelogram and the example involving negative numbers, the result of a determinant can be a positive number, a negative number, or even 0. If you get 0, it tells you something very specific about the matrix, but mathematically, a negative result is perfectly valid. Finally, if you ever feel overwhelmed by larger matrices in the future, just remember that the fundamental process for this order remains the same. It is a simple, 3-step arithmetic process involving exactly 2 multiplications and 1 subtraction. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session. I hope this summary helps solidify your understanding. Great job today.